And so I cry sometimes when I'm lying in bed just to get it all out what's in my head. And I feel it, a little peculiar. And so I wake in the morning and I step outside and I take a deep breath and get real high and I feel the top of my lungs. What's going on? And I say, hey, yeah, 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 hey, yeah. I say, hey, what's going on? And I say, hey, yeah, 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 hey, yeah, yeah. I say, hey, what's going on? And he tries. Oh my God, I try all the time in this institution.
Okay, well, on our research, we learned that actually that supposedly we evolved from monkeys. So which would mean that in like most photos that we saw and like on the research that we did, is that apparently the highest point was humans, which is us. But I don't believe that we're still evolving anymore.
So I don't think we would become any more creatures because I mean we're like the most developed of them all from all those stations that we've been through. So I think that this is the final station. So yeah.
In my own words, I think that evolution is a way of like transformation, but in like a way of like changing, but still have still have the same traits as like another person. So, for example, since we evolved, since we evolved from according that we evolved from monkeys or chimps, I guess we saw some traits as they do, which is like I guess some traits that we have are like because some of them are believed to be some of the world's smartest animals. So if we still have the same traits as they do, then I guess it's like changing shape or form, but not like the way that you think. I think that it's more before life, because if you look at it, we because like in the theory, it's that we started as a small animal and then we got bigger and smarter. So okay, and then we evolved into what we are now, which is humans. And so, and yeah, I think that's why I think that it's before the origin of life. Natural selection is, I believe, it's when it has to do with the offspring of animals because and if I'm not wrong, natural selection happens when two animals, I believe, I'm not sure, they like naturally choose each other to mate, and then that's when they have animals. I mean, like, but basically, baby animals.
For a process that's supposed to take millions of years, we sure do talk about evolution a lot. If we're going by the textbook definition, it's the process by which different kinds of living organisms are thought to have developed and diversified from earlier forms during the history of the Earth. This theory was developed by Charles Darwin, a scientist who gathered evidence for this theory on his voyage on the HMS Beagle. It was this voyage that provided the evidence for the process of natural selection. Another man known for his work in evolution is Chevalier de Lamarck. They both believed that life changed over time to better fit and adapt to the environment. They also believe that all organisms are related, and life evolved from fewer simpler organisms into more complex organisms. The difference between both of their theories is that Lamarck stated that the reason for changes in the organisms was due to the change of the environment. With this, he gave an example using giraffe. When a giraffe stretches its neck during its lifetime, it passes on this trait to its offspring. Darwin disagreed, however. He thought that these traits changed as a result of random traits given at birth. There is a primary technique of change over time which is called natural selection. This is the driving force of evolution. This theory was first brought forth by Darwin, and natural selection means that nature features the organisms that have a better chance at adapting to their environment and could survive long enough to successfully reproduce. There are different parts to natural selection, which are stabilizing selection, which favors an average phenotype, such as babies with average weight have a better chance of survival than babies underweight. Directional selection, a shift of the population of a species to another specific phenotype. An example would be the giraffe phenomenon. And lastly would be diversifying/disruptive selection, which selects again an average individual. Take peppered moths for an example. They're all light-colored in rural areas, helping them camouflage with their surroundings, while dark-colored moths in industrial areas can blend in with trees. This doesn't apply to gray moths, which don't blend in either area and get eaten a lot.
Now, to understand evolution, you have to know about abiogenesis, which is life coming from non-life, or the original evolution of life. To understand how Earth was before the beginning of life, Stanley Miller and Harold Urey began an experiment that simulated the Earth's conditions, calling it the Miller-Urey experiment. To do this, they used methane, ammonia, water vapor, and hydrogen. The most notable element was the lack of oxygen in the atmosphere, which at the time simply wasn't found. It was also come to know that amino acids were present, which are the building blocks of life, where there were none at the beginning of the experiment. It is thought out that this concentration of amino acids in the oceans of primitive Earth came together to form the world's first life. Because we've been blabbering away at evolution for quite a while now, I'd like to discuss the evidence that we as a society have gathered to support our theory of evolution. Because most of the meat is the theory of evolution has to do with the fact that all creatures come from a common ancestor before branching off. There are 5 main pieces of evidence supporting evolution that we found, and they are developmental homology, anatomical homology, molecular homology, fossils, and biogeography. First up, we have fossils. Fossil remains of ancient creatures that can either be imprinted into or turned into rock over millions of years. This supports a scientific theory due to the fact that remains of creatures were found in rocks, which allowed scientists to efficiently recognize the distinction from organisms in the olden days to the ones now present, and how through time they evolved. Next is comparative anatomy, which is used to compare and determine the relativeness of species from the first line. This proves that organisms' traits come from a common ancestor the same way evolution does. In comparative embryology, it shows that embryos of different organisms have similarities, implying that they come from a common origin. Biogeography, the study of distribution of life forms over geographic areas, proves as evidence of evolution by the fact that organisms which are closely related are found near each other unless there are good reasons, such as great mobility, which is flying, swimming, plate tectonics, some things along that line. Molecular biology supports evolution via the slow progress of species from other species by mutation in DNA. It's amazing how many things there are to learn about how and where we came to be.
As we do here on planet Earth, it can get quite difficult to keep track of it all. Thankfully, hundreds of years of biological studies have developed many systems to help us deal with a taxonomy, or classification. Our story begins with the father of taxonomy, a Swedish botanist named Carolus. He decided that the confusing organization by common names needed to stop. People were calling the exact same species by different names, which only served to confuse people. Carolus decided to create a universal system for organizing creatures with scientific names. These names use the levels of taxonomy, or taxons, which include things such as domain, kingdom, and genus to organize creatures by their internal structure and close relations. There are 2 domains, which are eukarya and prokarya. These consist of eukarya, which consist of all cells with nuclei. This domain includes every plant, animal, and mushroom in our world. Prokarya consists of every cell with no nucleus. This domain includes all bacteria, good and bad. Next up are the kingdoms, which divide organisms into animals, plants, fungi, and the like. After this we find phylum, which divides creatures by their basic body plan. After this is class, which is sorted by common characteristics or attributes such as mammals or reptiles, which leads to order, something that divides by further common attributes. including primates and whales. After this, we find families, which include groups such as apes and walnut trees. This leads into genus, which further divides according to an organism's close relatives, such as all foxes. Finally, we have the species, which is a reference to the single species, such as us humans. This led to Carolus establishing the method by which we use modern names today. First of all, the genus is stated, which is Canis for a wolf, for example, followed by the individual name of the species or familiaris. These are stated in italics, with the genus being capitalized, followed by the lowercase species name. Now that we've covered the methodology behind scientific names, let's go over how they've been used since. Originally, we used the classic method of classifying species, which depended solely on physical appearance instead of more realistic methods, so the phenotype. This led to scientists back then being a little off, if not at least taking a shot in the right direction. Thanks to our modern technology, we've changed our classification system to depend largely on the similarities we found between species. What we do is break down the DNA of two species into sequences of A, C, G, T and compare them to each other in order to figure out how close they may be.